Welcome back. Today we are diving into an absolute beast of an explainer. We're putting the Bass-Quillen conjecture through the ultimate mathematical stress test. This is a core pillar of algebraic K-theory, and we're going to see exactly how it gets definitively proven using the Adelic Langlands Program. We are going to use the mathematics directly from the framework to animate and guide our understanding, so get ready for a deep dive into some truly beautiful equations.
Here's our roadmap for today. We'll start with the Bass-Quillen conjecture itself, then model the algebraic knot, unroll the local factor, move into geometric erasure via GRR, hit holographic and spectral quenching, and finally, look at the complete proof architecture. Let's get right to it.
Part 1. The Bass-Quillen Conjecture. So, what are the actual stakes here? The conjecture basically states that every algebraic vector bundle over an affine space is a strict pullback from the base scheme. To really prove this analytically, the Adelic Langlands program lifts this whole module right into the geometric Langlands correspondence. If you look at the parameters, if the conjecture holds, the module is considered extended. That means its Hecke eigensheaf is totally invariant along polynomial paths, and its unipotent operators, they just act trivially. But, and here's the kicker, if a counterexample actually exists, what we call a non-extended module, it would show up as this wildly ramified, unipotent vortex with a local Swan conductor strictly greater than 0. Our game plan today? We're going to mathematically prove that the scenario in that non-extended column is literally impossible.
Moving on to Part 2, modeling the algebraic knot.
To track down this anomaly, we need to build a rigorous mathematical model. We do this by assigning the action of polynomial shifts, T1 and T2, to a pair of non-commuting upper triangular unipotent matrices in the local Galois representation space. Pay close attention to this specific term, delta p. That is our arithmetic twist parameter in the p-adic integers. If delta p isn't 0, well then our bundle is twisting away from the regular base ring. It represents our hypothetical algebraic knot, the exact suspect we're hunting down.
Now, because these polynomial variables do not commute in our hypothetical non-extended profile, we take their commutator in step 1. See how taking the commutator of TT1 and TT2 pops out a matrix with delta p squared right in the top right corner? Then, in step 2, we inject this straight into the Jacobson-Morozov theorem by taking the logarithm. And boom, that gives us the complete nilpotent monodromy matrix NBQ. Here is the absolute key insight. NBQ squared is not 0, but NB cubed cubed is 0. This highly specific mathematical behavior generates a 3-tier nilpotent filtration chain, totally confirming we have a higher-order unipotent vortex over the p-adic field.
So, just to summarize the flow here, this step-by-step Jacobson-Morozov injection forces a very rigid mathematical structure upon our suspect. We've essentially built our unipotent vortex in the mathematical lab. Now it's time to see if the framework of the universe will actually allow it to exist.
Section 3. Unrolling the local factor.
Let's put this anomaly through its first brutal test, the algebraic lens. This equation brilliantly illustrates how substituting the three-dimensional highest weight ladder into the determinant unrolls our explicit unipotent local component. We kick things off with the local partition factor, ZP. Since our monodromy matrix has a nilpotency index of exactly 3, the local Langlands parameter scales the Fabinho element by the diagonal weights, p to the 1, 1, and p to the negative 1. When we plug this straight into the determinant, we unroll the explicit unipotent local component, ZPSQS.
But look at what happens right here. This is where the stress test triggers a massive failure for our anomaly. Check out the exponent in the first factor, the inverse of 1 minus p to the power of 1 minus s. This introduces a rigid, supercritical pole exactly at s equals 1. In our thermodynamic framework, any pole sitting to the right of the critical UV/IR edge, which is where s equals 1/2, represents a supercritical, totally uncompensated energy state.
So what's the fallout? When we feed this local factor into the global integration, which is represented by x logos of s, that local pole at s equals 1 shifts the root number phase violently away from unity. And because the affine space geometry is completely smooth and contractible, it literally lacks any negative topological charges at infinity to cancel out this defect. The result? It viciously breaks the global functional equation. It requires a perfect topological mirror across s equals 1/2 that frankly just isn't there.
And here is the beautiful thing about this mathematics. The universe absolutely forbids this kind of anomaly. The absolute automorphic character of the partition function cannot be broken. The global functional equation is perfectly rigid.
So what's the only possible mathematical resolution? Delta P must equal 0. There is no other way. This forces the bundle to be a pure pullback right from the start.
Let's move right along to Section 4, Geometric Erasure via GRR.
Now we're going to evaluate the proper push forward of our arithmetic class. This powerful equation represents the arithmetic Grothendieck-Riemann-Roch theorem, or GRR. Because our affine space is completely flat and contractible, the relative Todd class just collapses down to 1. On top of that, by applying Stokes' theorem to a boundless domain, the integral over the complex non-compact coordinates cleanly collapses to 0. The result, the arithmetic GRR push forward completely and utterly erases those polynomial variables from the equation. To put that into perspective, this means the polynomial variables inject 0 net curvature, 0 net mass, and 0 net geometric deformation compared to the rigid base ring. It's like they aren't even there. Any localized field moving through this sector experiences the affine space as a perfectly rigid, flat, macroscopic baseline. This definitively forces homotopy invariance and, once again, demands that our twist parameter, delta SP, equals exactly 0.
Section 5. Holographic and spectral quenching.
Next, we expose our suspect to the final, arguably most complex tests, starting with the holographic lens. Here, we construct boundary-to-bulk propagators acting on the Brouhat-Titz tree. We're basically mapping local p-adic boundary fields directly onto the internal bulk nodes. If you look closely at the expansion of the operator-valued exponential term, you'll see that the quadratic component depends directly on our twist parameter, delta underscore p, which is embedded deep inside the NBQ matrix.
Now watch what happens as we move away from the boundary and plunge into the IR bulk tree. Our scaling depth n approaches negative infinity. Because of this, the logarithmic distance term also races toward negative infinity. So think about it. If delta p isn't 0, that quadratic term we just looked at is going to grow without bound. It causes a massive, explosive mathematical divergence right at the root vertex of the tree. And we simply can't have that. This divergence would inject an infinite energy density right into the logos stress energy tensor. For the global automorphic representation to even exist, the bulk state has to remain normalizable. So, to prevent this catastrophic infinite energy density, the mathematical framework necessitates what we call a forced trivialization dictate. It literally obliterates the unipotent drift entirely by, you guessed it, demanding delta p equals 0. Okay, pivoting over to the spectral side for our final test. We map the three-tier local factor onto the Arthur-Selberg trace formula via this global intertwining operator, m underscore p of s. By substituting our derived highest weight ladder into the ratio of local L functions, we get this explicit local scattering matrix operator, m underscore p of s. As you can see from the math, it equals 1 minus p to the negative 2 minus s all over 1 minus p to the 1 minus s. To find the actual spectral density, we take the logarithmic derivative of that operator along the critical line. Evaluating this highlights a critical term, p to the 1/2 minus I lambda over 1 minus p to the 1/2 minus I lambda. Because the exponent has a positive real part, evaluating this creates a highly localized, completely divergent spectral resonance. It's an explosive residue as the continuous wave variable lambda approaches 0. Now this directly violates trace normalization, which strictly requires a finite square integral continuous trace. The formula literally rejects this infinite energy, forcing delta p to 0 one last time. Bringing it all together now in Section 6, the final proof architecture. The stress tests are complete. We've tested the delta p parameter across 4 completely different mathematical domains, resulting in the total eradication of the non-extended state. Think about what we just saw. Algebraically, the global functional equation flat out forbade the uncompensated phase twist. Geometrically, arithmetic GRR strictly enforced polynomial erasure. Holographically, the Brouhat-Titz kernel mandated a bounded bulk state, completely rejecting logarithmic divergence. And finally, spectrally, the Arthur-Selberg trace formula rejected the infinite energy of that explosive residue. In every single domain, delta p was forced to 0. The nilpotent monodromy matrix is 0. The projective module is a pure pullback. The Bass-Quillen conjecture is, without a doubt, definitively proven within this framework. And I want to leave you with a thought to chew on. Is automorphic invariance actually the universe's ultimate bug-squashing code? The very mechanism that proves the Bass-Quillen conjecture once and for all? Do the rigid structural constraints of arithmetic geometry act as a sort of cosmic mathematical source code? inherently forbidding impossibilities from ever taking shape in reality? Thank you so much for joining me on this deep explainer today. Keep questioning and keep learning.